Recording now. Great.
Well, it's nice to be able to come here and give a colloquium, and thanks, Greg, for inviting me. And some of what I'll talk about today, I've got two different topics on different categories of work that I do, and some of you I know were at the workshop this summer. So some of that will be a little bit of a repeat, but there's actually some new results that I'll be showing today. So I'll be talking today about some work we do with electrostatic discharges, so the low temperature plasmas, and then also with work that we do where we shape high intensity ultrafast pulses and use the ponderomotive force to accelerate them. And that's what you're seeing in this this view, this little movie here, simulation in Osiris of that process. So, so first, just to introduce the people who are in the different research teams here. So there are several students that are working on the ESD project, and those who are in the bottom are the faculty collaborators. A number of them, I guess, John and Claudia are getting close to graduating, and Jonathan shortly afterwards. So Jonathan is Dan Adams' student. For the ponderomotive dynamics or acceleration team, Patrick Hunt is the main graduate student. Alex Wilhelm did a lot of the work that we'll present here. He's got a job at SpaceX now. He was looking at postdocs and then decided to go for the big bucks. And then I have several undergraduates who are helping out. Brian Gorman is faculty in materials, and Dan Adams is also helping me out on this project. I do have some other projects going on. One is in higher order harmonic generation. So we're using shaped laser beams to make higher order harmonics. And we have a couple students working on that project. And then we have a SCTR project with mesophotonics. We're doing four-dimensional characterization of ultrafast pulses. And then a student over at SLAC who is shaping ultraviolet pulses to create the electrons that are then injected into the linear accelerator there. And so he's sort of optimizing that work. Okay, so the talk is in two parts. First part of the talk is on the electrostatic discharge physics, and just a brief outline of what we're doing with that. We do a fair amount of work in modeling and then also experiment. And so I'll be talking about some of each of those things. And then afterwards, I'll move into talking about the ponderomotive acceleration. So the discharge process is, at first it's very simple in the sense that you have a high voltage. You take a free electron and it's accelerated by the DC field, and then the energy of the electron builds up to ionize more, and then you get an avalanche and you start the discharge. For those of you who work with fully ionized plasmas, working with low temperature plasmas, we talk about temperatures that are in the sort of EV level, several EV level. The plasma is not fully ionized, and especially if you're looking at discharges in air, there's a lot of actual plasma chemistry involved where you're dissociating molecules and they form new species, and that whole plasma chemistry side of things is actually quite complicated. And so the general process in what we're doing here is a situation where we have, we're considering, say, a charged object. It approaches the, some grounded object, and then we get the discharge, and then all of the charge that's stored is dumped over and transferred over. So the simplest model is sort of an RLC type circuit, as you see on the right. The key difference here is the so-called victim load is where the sort of the power would be dumped, but the resistance of the spark itself actually varies in time. So obviously we're starting out with a very high resistance. There's no conductivity, and then as you get breakdown, then the resistance changes, and eventually it will recover. So this area here or at least the work that we're doing, is sponsored by Los Alamos, and their interest in this is because they, as they're working with and around explosive materials for safety reasons, for very obvious safety reasons, they don't want anything to be set off, and so they're extremely conservative, as they should be, about the sort of safety procedures, but they're also conservative to the point where some of the assumptions they make are not even physical, in terms of like assuming that all of the stored energy on the object is going to be delivered into this the thing that might be damaged. But in the general field of low temperature plasmas, you could be looking at lightning or plasma processing. There's a lot of areas that are sort of adjacent to what we're doing here. So I'll step through in a little more detail the kind of steps of the discharge process. And that first step is that we have this charged object, and then you can just use electrostatics to figure out what the field distribution is. Okay, so it's not like we have, say, a parallel plate capacitor where you have uniform field. The geometry of the objects will give you field enhancements on axis, for example, if you have some sharper features. Say, in the next step, I used to use cartoons for these different steps, but now we're actually making pictures of the different steps. So these, I'll describe how we get these, but these are actual photographs of the discharge process at various steps along the way. And so the sort of initial breakdown of the gas is where you're accelerating those electrons. You're making more electrons as the energy of the electrons reaches the ionization potential. And you have to have secondary electron generation, in the sense that it's possible for you to create some electrons, and then those electrons you create on the very first go around entirely get swept over to the other side. Okay, and then everything could just stop. But you have to have a way to make more electrons, and that is either through ultraviolet being emitted by the plasma, or the ion return current that eventually makes its way to the cathode. As you start to build up the current, then you can form a streamer, which is a more concentrated discharge. You can see the narrow streamer on the right. Then you develop into. I'm sorry, I probably spaced out, but which is the cathode? Oh, I'm sorry. So in this situation, the cathode is actually on the bottom, and then we have positive, so we have ground on the bottom and positive on top. Yeah.
Is the streamer on the contour plot? Is the streamer depicted where it's really red?
The breakdown, the scale of things here would be that the breakdown is going to be anywhere in that sort of red and orange area, and then in fact, you can see that it's a little bit brighter at the anode on the top, which is where it's red. So that's where you actually have the most acceleration of the electrons, because the field is the highest. And then once you've later on, as things develop, then the current kind of concentrates into this streamer.
Is there a particular reason you're using a flat cathode and a rounded anode instead of the opposite, or?
No, we try both directions. We have been using unidirectional power supplies, and we just recently bought ones where we can swap the voltage. Just electrically speaking, you have to be careful about which side is ground. So you want to make sure your scope is measuring on the grounded side. So you have to be able to change the polarity. Okay, so then you go from the sort of initial relatively low current phase to a point where the resistance has really crashed. It's dropped down. You're really delivering most of the current through the arc at this point. And at this point, then sort of overall circuit effects start to kick in. Like, what is the inductance of the discharge itself, but also the inductance of the circuit that you set up. There's a lot going on in this phase here. You're starting to dissociate and make new species. That's when most of the emission is going on. And one of the things that we only recently started getting these kinds of pictures, and we're noticing features here where you can actually see like a really bright core and then a halo around it. So we're suspecting that most of the current is actually in that central core, but then the UV emission is actually doing excitation around the outside. It's either that or the shock wave that's developing is actually starting to create excitation on the way out. And so on a longer time scale, we get a shock wave, and this is a measurement that I'll show you in a bit, where we interferometrically measure the shock waves. And so the shock wave moves out. You're dumping a fair amount of the energy into the actual, hydrodynamic motion on the outside. And then these are some kind of cool pictures that we're seeing at later times. You can see a bit of a glow in the center, and then what might be some sort of Rayleigh-Taylor instability or something. This is at the microsecond scale. We're not really sure what's going on in these later times. But
Are you measuring this graph? Is this the neutral density?
that's actually the neutral density. Yeah.
And are you inferring that from light output or?
I'll slides on how we actually do that. But yeah, we also measure the electron density. We're doing this interferometrically, so we have a laser coming in from the side to probe that and look at the phase shifts.
And the photos are visible light?
The photos are visible light, and not right now at the moment we're not putting any filters on the camera.
Okay.
So the camera would be sensitive all the way down to about 200 nanometers in UV, and then out to maybe about 1 micron. So it's just spectrally integrated.
Yeah.
And we're imaging with mirrors so that we can actually see a clear picture across that whole wavelength range. And then the camera itself is gated at about 3 nanoseconds, so you get a pretty good snapshot of the dynamics. So some of the general questions that we're looking at here, programmatically, what our funders at Los Alamos care about the most is just sort of what are the conditions that will result in a lot of energy being delivered to what would be considered a sort of passive victim load, and how does that depend on the capacitance and other parameters. And then as we try to understand the physics of what's going on, we're trying to figure out, well, where's all the energy going? So it can go into ionization and dissociation, but it can also go into the hydro and radiation even. And so the more you understand where the energy is going, then the easier it is to come up with simpler models to describe how that nonlinear resistance depends on the current. Because if you can isolate one particular mechanism, then you can sort of make a simpler model. And then there's some plasma chemistry, as I was describing.
I have a quick question.
Sure.
About the shocks.
Yeah.
Have you noticed, like, in any particular parameters, you get one specific shock wave, and then if you tweak the parameters again, you get a different looking shock wave? Have you noticed similarities or differences with the shock waves?
Yeah, that's a good question. We are sort of at this point now able to see some of the details that are in the shocks, and so those are the kinds of things we're looking for, is to kind of understand the differences. So we have some modeling going on to describe the shockwave development, and there are some interesting features that we might see in terms of seeing a shock that goes out, but then there are also some waves that actually reflect back in, and there are other some interesting kind of dynamics that we might be able to see when we get more resolution in our pictures. So okay, so I'm going to go a little bit quicker at this point, but just to give you a flavor for the kinds of things we're doing on the modeling side. You can look in the sort of simplest view, which is sort of a so-called 0D model, where you're just sort of considering what are the dynamics going on in the sort of the plasma chemistry, but also just sort of treating things as I've got a fixed radius, a certain length, and you think of the whole thing as a wire, and everything that's going on inside is the same. And you can come up with relatively simple models for what's going on. Then you can sort of take another level of detail where you consider the radial dependence of what's going on. And this is where it includes the shock wave motion, but also diffusion and so on. And then you can go sort of full blown, higher, multiple dimensional type models Certainly there's dynamics going on along the length of the discharge. But you can also take it to higher levels where you're considering more in the way of plasma chemistry and looking at things from a big point of view. Those kinds of calculations are pretty heavy duty, but can also help point towards, are we missing any physics in the simpler models? And so that's kind of the approach that we take. So there's some simple pictures that you can look at where you just treat, okay, if I want to look at the resistance, what are the parameters that the resistance depends on? And the main things that it depends on is the size, the electron density, and the mobility. So those are the things that go into that kind of model. And there's some classic models out there where you'll look at one particular parameter and one particular energy channel. And so these are models that people have been using for a while. When I say a while, I mean like, since even the 30s or 40s. But those are sort of like the baseline models you use to compare to. What we can do is to either blend or improve some of these models where you actually allow multiple dimensions to change and include some of the hydrodynamics. And so you're seeing, an example of one of those things here. And, in the upper left, I guess that's your model for the shock wave, where you see the initial rarefaction waves moving towards the center. And then, this particular run doesn't show some of those sort of internal dynamics that are going on.
Can you remind me what EA is?
Oh, sorry. What's that?
There's electron ion collisions and then EA.
Oh, electron atom. Yeah. So those would be,
okay.
yeah.
So you have history.
Yeah, exactly. Yeah. So, and you can dive into these things at any level of detail. You could think of, I've got a fixed cross section for collisions, for neutral collisions, or you actually look at the actual data for, the energy dependence and average over.
But you're assuming like a formal populations or what?
And that's another level of detail you can go to in terms of looking at. Actually, I have some. Actually, this is a good example of this. So you can actually look at the actual electron energy distribution function inside of the DC field. So what you're seeing on the left there would be a skewed velocity or energy distribution function, where you have it, off center from zero because of the flow, and then you have some basically ballistic acceleration that happens of the electrons in the field that can skew, give you a longer tail in the field in the direction of the acceleration. So these are models that are done in COMSOL, which is a finite element type platform. So on the experimental side, what we're doing is to we have a discharge chamber that you see on the left, and inside the use this. So we've got our two different electrodes. Here we have just two spheres that are installed. And if you zoom in on that, this is the actual discharge in argon that we see. And so in this chamber, we've got windows, and we can put in whatever gas we want at whatever pressure. You have to make sure you don't get breakdown to the outer walls, but that's a pretty flexible setup. And then
how big are the spheres?
so this scale here, this whole thing is probably about a foot high, and the spheres are maybe a couple centimeters radius. Just give you a sense.
Claudia was at the SIPS retreat, right?
Excuse me?
Claudia was at the SIPS retreat, right?
That's right.
Okay.
Yeah. So this is her setup. Yeah. Yeah. So she did all the design of this, and we made it in our shop. And so how far apart these are ranges up to about a centimeter. Obviously, the bigger the gap separation, the higher the voltage you need to be able to run at about 30 kilovolts per centimeter breakdown threshold. Then that sort of gives you a scale for the kind of voltages we're running with. And so we can measure. There's a what we call a CVR, which is current viewing resistor. It's just a fraction of an ohm resistance that's in here, and that's like a witness resistor that we use to measure the current. And then we also have a fast probe to measure the voltages at the top here. And we're charging through a current limiting resistor. And so just an example of some of the energy or the sort of electrical type measurements, is you can kind of look at how things scale in terms of how much energy is delivered to the, or what fraction is delivered to the victim load as a function of these different parameters. And so you can kind of use one of those simple circuit models as a baseline to see that you would have an energy delivered that would be linearly dependent on the capacitance, which affects the amount of energy stored. And so there's some ways you can kind of see how things scale here. Another experiment that Claudia has done is to set it up so that we have a secondary capacitor on the side, because that gives us a way to trickle in some current after the main discharge. We can actually keep on going, adding a little bit of current, and then you can see, well, how long does it actually take for the channel to close? And that's going to be over on a longer time scale. Before we did this, we had no idea like how long it would take for that resistance to end. And what you're seeing in this plot here, this is the actual data we collect. So this is the voltage across the top, and then this is the this is the voltage measured here. So this is across the secondary capacitor, and that's just a simple sort of RC decay. And then this is the current that we measure, or sorry, the voltage that we measure across the gap. And so when you work it out to get the resistance over here, then we see different phases of the resistance starting very low on a few ohm resistance, and then on a what are we at here? So I think we're at about 10 microseconds is when there's a faster rise in the resistance, and then a slower rise. And so we're still working on trying to figure out what's going on, but the initial thought is, okay, well, we have 3-body recombination at first, and then we have maybe a radiative recombination. But it turns out through our imaging, we actually end up seeing that the electron density is actually not changing that much in some of these phases. I can't remember which one. I think it was the earlier phase. And so the resistance is actually probably climbing more because of the cooling of the plasma, which actually changes the collision rates and gives you a higher collision rate and more resistance that way. So
T = 0 is when the plasma is formed.
that's right. That's when the discharge actually happens. Yep. So other diagnostics that we have is, we can look at the emitted plasma, the emission from the plasma. And we're working on sort of getting better calibrations for our spectrometers so that we can get, this one's pretty good here. We're doing some other spectrometers that we're calibrating, but basically using a calibrated source so that we know what the actual relative amounts of emission are across the spectrum. And then that way you can infer maybe a black body temperature or recombination emission spectrum. And so, so in this type of image or spectroscopy, what we're doing is we're measuring with a photomultiplier tube at a given wavelength, and we initiate a spark and then see what the time history is at that wavelength, and then doing that for a whole collection of wavelengths. And that way we build up a whole sequence for the different gases of the spectrum, going all the way from 200 out to 900 nanometers. And with this kind of thing, you can actually see in some of the early phases, like in nitrogen or air, in this range here, these are the sort of N2 molecular emission lines. And this is prior to breakdown. And then when you get it to break down, then you get your continuum. This is during the main arc. And then as things cool down, then you see a bunch of other emission lines show up as things start to recombine. So there's definitely a lot going on in here, and we haven't really fully analyzed like all the different species. What you're seeing in these lines here, those are just sort of the tabulated atomic emission lines you get from the NIST database. But there's all kinds of molecular lines as well. So there's a group over in Los Alamos that does sort of atomic physics, and they're helping us with some of that interpretation. So, so the other thing that we're doing is to work with interferometry And the way that's set up here is just a simple Mach-Zehnder type interferometer. And we take our laser source coming in this case from the right. We have two different wavelengths. And the idea there being that when we do the interferometry, we're measuring a phase shift as you go through the plasma relative to the reference that goes around the chamber. And if we measure the phase shift at two different wavelengths, then that actually gives us a way to tease out the difference of different contributions from the neutrals versus the plasma. So we get the free electron contribution and then also the neutral contribution. And then that way we can get a evolution in time of the electron density for each of those two different categories of species. And so we do get our interferogram, we go into the Fourier domain, pick out the sort of the modulated side lobes and go back, and then that gets us our phase profiles. And when I summarize it in that way, it makes it sound easy. But when you're doing things and trying to get real numbers, and you're also taking differences of phase profiles, it's pretty hard to get it right.
How many of these pictures do you get per second, or I mean, is it
Yeah,
one shot? Or
yeah. So it depends on the camera we're using. So the one that we own is a single frame on a shot. We can borrow one that gives us 256 in one shot. And so the fancier camera is like a couple $1 million type camera, and so we don't get it all the time. But some of the images that I'll show you, actually, this one right here, these are from that Shimadzu framing camera. So you actually get a movie of the shock waves on a single shot. And so it's very useful. Unfortunately, the minimum exposure time is about 50 nanoseconds, which is pretty short, but it's not short enough to capture the motion in the earliest phases. Which is
say
one of the
15 or
50.
50?
Yeah, 50. And then it's 100 nanoseconds in between frames, or at least between the start of each frame. And so we do these different measurements. These measurements here are from a single shot, and this is newer results, where we see if you look closely, you see the finer or more closely spaced fringes for the short wavelength compared to the longer wavelength. And you can see the distortion of the fringes, and we analyze that to get the phase that we're retrieving across. And then what you do is you're actually looking at a projection of the phase shift through this assumed cylinder, and you do an oval inversion to get the radial dependence of the refractive index. And then you combine those measurements of those two different wavelengths to get at the profiles for the electron density and for the neutral density. And so one of the things that's kind of interesting about this, and we're still trying to make sure we're understanding this correctly, is that number one, the shock wave is in the neutrals, and that kind of makes sense because you actually got this pressure that kind of gives an impulse to the neutrals on the outside, and the shock wave runs out faster, as faster as speed of sound. It runs faster than the fluid flow going outwards, and so it leaves behind the plasma core, so the electron density is concentrated in the center. The other thing that we're trying to fully understand, but this bump in the center for the what we're considering is the neutral density. And what we're assuming is that the neutral density or the neutral gas has the same refractive index as air, but inside the central part of the hottest part of this plasma, there will be a lot of dissociation and also excitation. And so the sort of working theory at this point is that because of the dissociation and excitation, then the refractive index of that of those heavy species is actually quite a bit higher than it would be for just ambient air. And so what we're expecting to see as we take more measurements is that bump there would go down correlated with the emission that we see as those excitations die out. So that'll be interesting to see how that goes.
Do you get these profiles as a function of time, or is it just one single time shot?
At the moment, we are getting them at one shot because the spark triggers our lasers that we're using trigger is a nice way to say it. That the noise pulse is actually what is getting the lasers to run. We're working on isolating the noise from our electronics so that we can actually control the delay. And so we're making Faraday cages and shielding our cables and doing all those things that we have to do. So we're making progress on that actually. So some other sort of types of imaging that we're doing are working with, this is Dan Adams' work and his student Jonathan Berlack, where you use computational imaging instead of interferometry. And this is sort of in the development phase, but it's kind of interesting because it's a method that actually gives you the illuminating beam as well as the object phase profiles. And so one of the experiments they've done recently on a different system is actually 2-photon absorption in zinc selenide, where you basically end up getting a free electron gas, if you will, in the conduction band of the zinc selenide. As you pump it, what you're seeing here is the image of the phase profile prior to pumping, and then you pump, you've got a delayed pulse, about a nanosecond delay, and you can actually see the decay of the electron density out of the conduction band over this kind of time scale. So this is an example where you have one camera, it's not gated, but you actually have 4 pulses hitting the camera, the same camera, and you can actually tease out the contributions from each of those different time frames, because each of the beams, it's a little bit hard to see in this picture here, but each of those beams is actually tagged with a different amount of orbital angular momentum. And so that gives you a way to kind of separate those different frames out. So our latest work is to trigger the sparks with ultraviolet, and that's how we're getting these images at the earliest times. And essentially, you're hitting the cathode with some UV to make some electrons, and then you trigger the spark that way. And this is how we're getting all these different kinds of images. These are all separate shots, but you can see there's a lot going on in the early time frames. And there's a lot of interesting dynamics to look at.
Looking at this slide, I guess where would you draw the line between the streamer and like your arc? I mean, is that synonymous with spark? Spark and arc are used interchangeably?
Yeah, we're kind of working on making sure we have all of our time calibrations correct, but my interpretation is that this is sort of the avalanche phase, and then these are both, and this is sort of like, merged going from avalanche to streamer. This would be a streamer, and then this is the brighter arcs.
Okay, so once it starts broadening,
That's right.
And do you know rough current values for each of these phases?
I'm not exactly sure on these specific ones, but the current profiles tend to be, these are the current traces themselves. And so for this particular run, I'm not sure if like this gap is the same as the other one, but you're looking at, things starting up at around 120 nanoseconds or so. And then the main current is on that first peak. And then the ringing is because of the inductance in the system. So you get some sloshing back and forth. But the main energy delivery is in that first peak and a half. This is where you depositing most of the energy is causing. Okay, so so we're just doing a bunch of different aspects of this problem, and this is kind of a summary of those things. I've already gone most of my way through the talk here, so I'm going to move on to the next topic, which is to look at the tilted laser pulse work. And so what we're doing with this is to find ways to accelerate electrons, and you've probably heard about people who do, say, wake field acceleration. In that process, you're using the ponderomotive force of the intense laser pulse to expel the electrons from where the pulse is, and then as the pulse propagates forward, then the electrons kind of rush back in, and you get a very strong electric field in that wake. And that wake field can be driven by a laser, or like Mike Litos does, is to drive with a particle beam. So in this case, the strong electric fields, which are very strong, are coming from the plasma. A direct field approach is one where you're using the electric field in the optical field to directly accelerate. And this is kind of like the Holy Grail in the sense that the field strengths are incredibly high for the short pulses, But the main sort of challenge here is the dephasing of the field with the electrons. The electrons don't go exactly at the speed of light, and so you can't be on a certain peak within the field. So that's the challenge there. What we're working on here is a technique for using the ponderomotive force to accelerate. And the sort of force gradients you get are not nearly as high, but you can accelerate from 0 up towards c. And then the application would be to then take those electrons and then inject them maybe into a wave field type accelerator. So our approach here is to use the tools that we have to manipulate the laser pulse to actually create a pulse that actually travels through space with a tilt, which is a little bit weird, that you could do this, and I'll explain how that works. And then because of that tilt on the pulse, then the sort of velocity of the force as it moves across the electron bunch, it slows down the interaction in a way that allows those electrons to sort of catch the wave, so to speak. And so in this approach of the way that we're creating these pulses, we have the full bandwidth and short pulse at the focus, but then we get this tilt in the pulse. And so we're looking at accelerating kind of in the range of 10 keV up to several MeV kind of range. That's the kind of application that we're looking at. And so we could use that for injection into other accelerators. We also have, as part of this project, we're putting in a laser triggered electron gun where we can actually inject electrons in vacuum and accelerate them. And this will be really interesting to be able to explore the sort of whole ponderomotive acceleration process and hopefully use those electrons for electron diffraction. Okay, so how does this actually work? So I'm going to assume that most of you are not laser people, but our short pulses have very broad spectrum. And we intentionally have what we call a spatial chirp, where we actually have those spectral components parallel to each other out of the compressor, which is used to make that pulse short. And so when you change that separation between the gratings, you could have some pulse front tilt if it's under compressed. We're using our pulse so that it's actually compressed in the sense that each of the spectral components comes out at the same time. But the pulse isn't as short as it could be because those spectral components are not actually on top of each other spatially. So then what we do is we focus that beam and bring all those spectral components to be overlapped in the target plane. And in addition to having more bandwidth at the target plane, then the angular dispersion you have actually gives you a different chirp as you pass through the focus. And so the easiest way to understand why that happens is that if you just look at the phase of a tilted plane wave, okay, and now we have a situation where the different spectral components are actually going at a different angle. That's what this theta of omega is. And so if you look at the blue term, this is the z component, the forward propagating component of the k vector. That actually has some dispersion in it, some spectral dependence. And when you calculate the dispersion by doing the second derivative of that spectral phase, then you end up with a chirp, which is in the sort of time direction that varies with z. So in other words, your pulse is fully compressed at the focus, and it's negatively chirped on the way to focus and positively chirped on the way out of focus. In addition to that, you also end up with a arrival time of the pulse at the focal plane that depends on position, and that is your pulse front tilt. And so it's a little bit of detail here in terms of how we make these tilted pulses, but that detail ends up mattering when we're looking at these tilted pulses. So that sort of summarizes that, but I want to talk about the mechanism for the acceleration. So you can think of the ponderomotive potential of the pulse itself just as a potential hill that tracks the intensity distribution of the laser. Okay, so we're looking at an acceleration mechanism that doesn't require any plasma to be there. It can be, but we're not using that directly. And so if you had an idealized model of a tilted pulse where you don't worry about the spatial variation in the transverse direction here, then you can actually calculate, well, what direction is the force? It's going to be in the direction of the steepest gradient. And the actual velocity of that force is decreased by the cosine factor of the tilt. And so what you're able to do is to decrease the interaction velocity from C to something lower. Now, why does this actually help? If you have a potential that's moving at C, then the electron will start to move, but it goes up and over the potential. If you can slow it down, then it can actually catch the wave.
I'm sorry, I'm confused about why it isn't C over cosine theta. Is that
Right. So what you do is you write down the expression here for the tilted field in the lab frame, and then you go to a sort of rotated coordinate system, so x prime and z prime. And what you see here is, so we're looking at is what is the velocity? So we are dividing by cosine, but it's c times that. That's the effective velocity there. So I'm not sure if that answers your question directly or not, but
so? What direction does the wave pulse propagate?
yeah. So the
Propagated
wave is going in the lab frame z. Okay.
Oh, okay.
But in this sort of infinite width approximation, then if you're in the rotated frame, then it's as if the since there's no features in the transverse direction in this simple model, then it doesn't matter physically where along the pulse front the electron is. So it does slide along the pulse front some, but in terms of the acceleration is only in the direction perpendicular to the pulse front itself.
I see.
And so that allows that velocity to be less than c. Yeah, it's not super obvious. And so when you look, then you can go in the simple model, you could be in a frame of reference where the potential hill is not moving and the electron's coming in at it. Okay, and so just simple mechanics, you'll see the electron coming in from the left. This is sort of the limiting case where it is just at threshold, where it goes up the hill and then back down. And so really it's just a simple, I'm starting in this model, I'm coming in with this velocity and I leave at that velocity. And so the delta in velocity is 2v, and you square that for the kinetic energy, you get 4 times that. 4 times the kinetic
And
energy.
presumably there's some initial condition that the electron would just split.
Right.
Not
So
get caught up by
if that intensity is lower, the hill is smaller, and that electron would just go up and over. Yeah. So it's just like if you're trying to catch a wave and you're surfing, and the reason why you paddle to catch the wave is otherwise you just go up and over, unless you are unfortunate enough to be in a tidal wave where it catches everything in its path. But this is basically the tidal wave of that. Okay, so way to kind of picture this here, and there's some relativistic corrections you have to go through, which I won't spend time on in the moment, but there's basically an intensity of capture, and when you're at that capture threshold, then literally all of the electrons that are in its path will get swept up and then ejected off to the side. And so this is where we start having to confront reality because we don't have an infinitely wide pulse front. And so we have to kind of look at some more of those details. This plot just sort of illustrates, if you're below threshold, then you're left with an energy. You're left with an energy here on the output that is back to 0. And then once you've reached threshold, then it actually doesn't matter whether the intensity is higher or lower. That threshold actually just depends on the angle. And so that's actually a useful feature because your pulse intensity is going to vary, across the beam profile. And as long as you've captured it, and as long as that tilt is flat, then the electrons come out at the same energy and the same angle. So this is where, we start worrying about the actual effects of the beam shape. And the main upshot here, because I'm getting low on time, is that the flatter the profile, okay, it's the flatter that pulse front is. If I look at a given contour, let's say if I look at this one here, there's actually a contour that's kind of convex. It's a little bit hard to control here, but you could think of that surface as a mirror that is reflecting those electrons out. And if that mirror has some shape to it, then those electrons are going to come out at different angles. Okay, so that's one important effect. The other important effect is that if an electron starts, let's say at the middle, then as it's being accelerated, it's going to be rotting for some amount of time. It's going to be rotting along this tilted front, and it might just pop off the end. And if it does, then then that doesn't help either. And so what we have to worry about is what is the actual sort of shape of that intensity profile as a function of time. And this is where some of the details of just the optical physics of how these pulses work come into play. And so you can end up with a situation where you have either a convex or a concave kind of surface, and those effects actually will result in different directions for those electrons. So you could actually use it to focus electrons, or maybe they're diverging. In any case, you'll end up with kind of a correlation between the output angle and the output energy. And so that's part of what we're hoping to see when we do this experiment. So just a quick aside, we're using OSIRIS right now for our modeling, and it took Alex Wilhelm quite a while to actually be able to get our pulses into that code. And we essentially had some sort of I think they call it an antenna feature that's on the far left of the boundary, and you use it to emit different point sources. We actually constructed the field from that by adding up all these different wavelength components. So that took a lot of work. The long story is that I was trying, when I got funding from NSF, I was trying to use Vorpal at the time, and Slava Lukin at NSF didn't want to fund the commercial code when he was already paying for OSIRIS to be developed at UCLA. And so that cost us a few years in development time. But using that code, we can actually look at the actual process, and you can see here a situation. If you look closely at the electrons, they're actually being focused from this concave surface. Actually, I'm sorry, I don't want to mislead here. Part of what we're looking at are different densities. And so we have a focusing situation, but then as we go to higher densities, then the Coulomb repulsion within the bunch itself actually can compensate for that focusing. That's this bit here. And then even higher intensity, then you see the Coulomb repulsion just blowing those electrons out. So there's a lot of interesting dynamics to look at. Okay, so as I finish up here, we have beam time at the ALEPH laser up at Colorado State in December. And this is the sort of petawatt system that they have that Jorge Roca has put together. And so we were able to convince them to let us go in and build them a new compressor to make these tilted pulses. Normally people go to a laser like that and they do whatever they want to do in the target chamber, and they turn on the beam and they do stuff. Here we're actually getting into the system, and this whole setup that you're seeing here, that's our compressor that we're building, and then we'll do our experiment in the chamber. So we're going to have 2 weeks to install the compressor, and then another couple weeks to take data. And so just to summarize this part of what we're doing here, so we're using these shaped pulses to do the acceleration, and we're excited to actually try that out up at this laser at CSU. We are setting up experiments in our lab also, and those will use this electron gun, and we'll be looking at things at lower energy. Our laser is only 10 millijoules per pulse instead of 10 joules per pulse is what they have up there. And then, so we're doing experiments in our lab as well as up there. And so I am looking for a postdoc for anybody who knows anybody who's looking. Our recruiting people requires me to put up our advertisement just for general for PhD students. If you guys are working with any good undergrads who might want to apply, then send them our way. So, but thanks so much for the opportunity to speak there.
Thank you.
It's been great.
Great. So any questions?
I have another meeting time to go.
Okay. All right.
Seeing you again.
Okay, let's see again.
Yeah, I have a question about the experiment. So when you do experiment, will you just send it in vacuum and shoot electron in, or you will fill with some gas?
Yeah, that's a good question. In this particular experiment that we're running up at Colorado State, we have a gas jet, and the gas jet is going to be placed right at the focus of the laser pulse. For the experiments that we're setting up in our lab, we'll have an electron gun that will make a bunch of electrons that we produce, initially with one of our laser pulses timed up with our laser system. And then in that situation, we'll be in vacuum and then sending the electron bunch and timing it up with our laser pulse.
So if you have a gas jet, would it be a problem if you start ionizing stuff on the gas jet?
Yeah, well, we certainly don't want to hit the actual nozzle, but the electrons that we're accelerating are actually produced from that ionization. And so we'll be using helium and just fully strip the helium. So as we get up to higher density, then the space charge effects will become important. And so we'll be doing our initial experiments in a kind of a range where that Coulomb attraction to the ions that we're producing is not important. But we are looking at a situation where we're in the other regime, where instead of accelerating the electrons will snap back at and oscillate at the plasma frequency. And then we would look at terahertz emission from those oscillations.
Thank you.
Sure.
Any other questions?
Yes, I have a question about.
Yeah.
A couple of questions.
Yeah.
Breakdown. So first, just out of curiosity, I've seen tables for spark gap breakdown voltages, like 2 centimeter spheres or something.
Right.
And are those accurate? I mean, they look very precise, like they'll give the voltage and distance at which it breaks down.
Meaning just sort of like if you make a plot of what the breakdown voltage is as a function of the gap.
Right.
Yeah.
I
So
wonder whether you would trust those tables. In my experience, breakdown is very messy and
right.
have a very wide ranges.
They're pretty good, I would say. There's some definite dependence on the electrode shape. So when you have say a plane parallel type situation, which is not normally what you have, then there's no like field concentration. But like in some of the pictures that I was showing, you have an asymmetric situation where the field is actually concentrated more on one electrode than the other, and so the breakdown potential is actually lower for those situations because you have that field concentration. And so those effects matter more as you expect, the more that the kind of radius of curvature of the electrodes is important relative to the gap. So you could go to a really small gap and not worry about those effects. But I would say that's probably the biggest effect on that breakdown potential. Another issue might have to do with just how many electrons you just have floating around, which might be very small at first, but if you're doing it repetitively, then what happened on the previous one might affect, where it starts to break down just because there's still some plasma around.
And so I was interested at first I thought that the goal of that project was going to be to figure out when breakdown would happen. But it sounds like you're more interested in worrying about what happens after breakdown is
That's right.
initiated.
Yeah, that's right. So that the voltage where you get that breakdown is not, there's not that much that isn't understood about that. But the actual dynamics in the very early phases of the spark, there's still a lot going on there that people don't fully understand. And then, so we try to do, we're funded to do work that helps their program at Los Alamos, but at the same time, we try to do some physics too. And so the physics side of things are the spark dynamics and developing these diagnostics. And then the sort of programmatic side of things is sort of understanding what it is that influences how much energy can be deposited into something that might be damaged by it. And that and we're getting pretty close to done on that side of things.
So that's that with the goal of mitigating the damage or implementing, like adding some sort of, I don't know, safety mechanism, high resistance or something that would limit the amount of energy.
Yeah, so that's right. So you might have a situation where for instance, for a certain object that is physically a certain size, then that actually will control how much charge you can even put on it, because as you put more and more charge on it, then you get corona breakdown and kind of a self-limiting kind of effect. And so as you go, if you're working with objects smaller than a certain size, well, there's only a certain amount of energy that can be stored on those objects. And then also you can only be in a certain type of discharge regime because that energy is smaller. And so in our lab, we actually just use capacitors, and we're trying to step it up so that we can see where those boundaries are. So even if it's outside of the range that they care about, we can at least say, okay, well, you guys are 5 times under this other regime where the breakdown is even lower resistance. So
What kind of, sorry,
Yeah,
what kind of power supply are you using for your breakdown experiment?
So we have been using fairly well combination. One, initially I was thinking, just because I've used these kinds of power supplies for charging capacitors for flash lamp pump lasers, and so there are capacitor charging supplies that you can get. And I got one of those, but then realized that was way too fast a rate of charge than what we would want. In other words, it delivers the charge in bunches, some sort of switching supply. And so we're switching over to sort of a more modest current, steady DC current supply that will charge to a better targeted voltage. But we're working on also on a charging system where we can kind of charge something up and then actually stop charging, so that when we get the breakdown, then we can tell it to start charging again, so that we don't sort of do a repetitive discharge, so we can control how much time we have in between the sparks. So that can matter too.
Any more questions? Great, if not, let's
All right.
thank Chip again.
Thank you.